Hey guys, okay, so we're back with lesson 3.3 and the ending. So we're finding the bases of the image in kernel using the reducer echelon form. So here I've drawn out a matrix and started to draw out the reducer echelon form, which I'm going to proceed to finish doing very quickly. 4, 5, 0, 0. Okay, so we've got this reduced row echelon form, right? Well, it's very easy, of course, to come up with the kernel, right? The basis of the kernel. Because, of course, we end up just writing, putting in variables, putting in letters to represent the free variables that we have, pulling those variables out from the columns that we've created, and you end up with something like this. 0, 4, 1, 0 plus R 4, 0, -5, 0, 1. Okay, well now that is easy, right? However, what about when we're trying to do the image, right? Before, we have not used the reducer echelon form for image. We have used the original form, right? And we found the columns. Now, to construct the basis of the image, right, we need to find the redundant columns of A. Well, we can use B to do that, right? And the way that we do that is we look for, and here's where we get into our theorem. If we draw out, and I'm going to draw it out bigger this time, if we draw back out our reducer echelon form 1, 0, 0, 0, 2, 0, 0, 0, 0, 1, 0, 0, 3, -4, 0, 0, -4, 5, 0, 0. So we draw this back out again. Now, the proof that we're about to get to is that when you construct a basis of the image of A, you need to pick the column vectors of A that correspond to the column vectors of the reducer echelon form of A containing a leading 1. So what here contains a leading 1? So these two are the only vectors that contain leading 1s, right? And then if we were to see that corresponds to which reducer echelon form, well, it corresponds to the column vectors of the original that are 1, -1, 4, 3. And what's the second one? 2, -1, 5, 1. And that would be the basis of your image. Now, why does this work? Well, basically what we can say is that these columns correspond to the reducer or echelon form columns, right? And so if something in reducer or echelon form has a leading 1, right, then that means it is not redundant, right? And so if it's not redundant in the reducer echelon form, then that means it's also not redundant in the original form. So those are your two non-redundant column vectors, which of course are going to be the basis of your image. So that leads us into a theorem that I'll just write out. So for using the reducer echelon form to construct a basis of an image, thing that you want to keep in mind is pick the column vectors that that correspond to the columns of the reducer echelon form of A containing leading 1s, right? So that's kind of our theorem for that. So we did already talk about using just the normal matrix, not the reducible echelon form, to find the image, right? And then from there we can find the basis. Well, that one takes time because you have to identify which vectors are redundant using some more complex methods. This one takes time because you have to do reducer echelon form first. So, I mean, they're all viable options, right? It's just, I think, which one makes sense in whichever scenario, because both of them take time for different reasons, right? But what we're going to move on to talking about now is the dimension of the image and the dimension of the kernel. So the dimension of the image, we've got a theorem here, which is that dimension of the image of A equals the rank of A. Okay, so why do we know this? Well, that's because of what we just said about the leading ones, right? Well, the number of leading ones is, of course, the rank of something, right? Well, we've just said the dimension corresponds to the number of leading ones in the reducer echelon form. So that means that these two things must be equal. Now, if we want to talk about kernel, let's think about this definition. We know that the dimension of kernel equals the number of free variables, right? Well, that can be broken down into the total number of variables subtracting the number of leading variables, right? Which leads to m minus rank of A. Because m, of course, is your total number of variables, and the number of leading variables, of course, is the rank A. So if we combine these two equations, right, we can say that the dimension of kernel A plus the dimension of image A equals m. Well, why can we say that? So we can say it because, we already pointed out we've got the dimension of kernel A, or we can say that because we've already kind of figured out that if we've got rank A, we can plus rank A and move it over here, and rank A is another word for dimension of image A, right? So this leads us into the rank nullity theorem. Now I'm capitalizing it because it is known as the fundamental theorem of linear algebra. And the point of this theorem is it takes this dimension kernel and dimension image thing and writes it a little differently. It ranks it in terms of the rank and nullity. Well, first you must understand the dimension of a kernel is called the nullity, right? So it's just another word. So we have the nullity of A plus the rank of A equals M is kind of our big theorem. And of course, you can rewrite this around a little bit, which leads to a really interesting example. You can write it as M minus the dimension of kernel A equals the dimension of image A. Now, that one is a very interesting way to write it because it leads to this example. And this example being a plane that we are given and we are told that this right here is T of X, that this plane is the image of T, that this is X, and this is the kernel of T. Or in other words, the thing that is perpendicular to V. Now, here's an interesting way that we can think about this. If we take this equation, M minus the dimension of kernel T equals dimension of the image T. Here's what's really interesting. This right here can be thought of as the total, initial dimension, right? The total number of variables, the initial dimension. Then this right here, the dimension of kernel, can be thought of as the number of dimensions that collapse. I'll explain this in a minute. And finally, this can be thought of as the number of dimensions that survive, right? So what exactly do I mean by this? Well, you start out with m dimensions, right? Well, but then you subtract the dimension of kernel. Well, the dimension of kernel is the, well, if we think about it, it's the solution, right? It's the things that map to 0, right? So that means that it's the number of dimensions that collapse, that aren't sustained, right? And then if you subtract the total minus the number that collapsed, that leads to the dimension of the image, the number that survive. Let me show this in action, kind of. So we start out with dimension being 3 because this is a plane in R3. The book tells us that. Then the dimension of kernel T is 1, right? Because this is a line, so its dimension is obviously 1. And then we end up with a dimension, right? If we do 3 minus 1, we end up with 2. Well, does that make sense? Yes, because we end up with a plane. So obviously dimension is going to be 2. So you see, number you start out with, the number that collapses, the number that survives. All right. Okay, so the next thing that we're going to talk about really quickly is the idea of using the matrix to find the bases of the imaging kernel, something done a lot of times, but instead thinking about the kernel in terms of linear relations. So we start out with this A. Okay, so we started with this, right? Well, we end up with these redundant columns, right? With V1 equaling 1, 1, 1. Sorry, these are the columns that are left over after we get rid of all the redundant ones, right? 1, 2, 3, 4. So this, of course, is the image. To get the kernel, we can think about things slightly differently. Let's take our redundant vectors and make them into linear relations. So the first one we have is that V2 equals 2 times V1. Well, if we made that into a linear relation, it would be 2V1 plus V2 is 0. The next one is that V3 equals 0. And finally, we've got that V5 is equal to V1 plus V4, which would be written as negative V1 minus V4 plus V5 equaling 0. Okay. So if these are our linear relations, what can we do with this? How does this relate to the kernel? Well, the book explains that we can take the constants, or the coefficients out of each one of these relations and make them vectors. So the first one, negative 2, 1. Sorry, 0, 0, 0. You have to take into account all the other components. 0, 0, 1, 0, 0. And finally, negative 1, 0, 0, negative 1, 1. I'll highlight these just so you can see it a little bit better. The span of all of these is your kernel. Right? The span, and I'll repeat that again, the span of all of these is your kernel. Another way of looking at the kernel, right, is all of the coefficients of the linear relations. Now that should also make sense. The reason why is because, all of these things are equaling 0, right? Well, the point of the kernel is it is the x values that map to 0, right? That lead to the zeros in the image of the function, or sorry, of the linear transformation. So these are all things that lead to 0. So it makes sense that their coefficients that the span of those coefficients, right, would be 0. So that is your kernel. And you can also, that leads to a theorem. I'm gonna clear all of this. The theorem is that finding the bases of the kernel and image by inspection. Okay. So this basically is just a way of writing it out, but it says that express each redundant column vector as a linear relation and generate a vector based on the coefficients. Now, you have to find all of these relations and all of these different vectors to be the full kernel. Okay. So the last thing that we're going to quickly talk about is another way of looking at bases, which is another theorem. So the bases of R to the n. So this theorem states that that vectors Rn form a basis of Rn only if and only if your matrix is invertible. Now, the book does have a proof for this, right? So we already know that the vectors are a basis of Rn if and only if every vector in Rn can be written uniquely as a linear combination of the vectors of V1 through Vm, right? And a way that we can write that out is like this. We've got our matrix made up of V's. Right? But this linear system has a unique solution for all B if and only if this matrix is invertible, right? So for the definition of a basis to be true, this matrix has to be invertible. Then we've got a quick example when it asks for which values of the constant kh of the following vectors form a basis of R cubed. I'm not going to run through the example, but I will just talk it out really quickly. What they did is they formed a matrix out of these vectors, right? And then they solved for all the places where they solved basically to figure out when the determinant would equal 0, with what k values the determinant would equal 0. And so their point was it's a basis for all the values that are not the ones that make the determinant 0, because that's what makes the matrix non-invertible. So we are going to stop there, but I'm going to recap really quickly what we did. So we talked about, sorry, I'm flipping back through the lesson here. What did we even talk about? Okay. So we talked about the idea of spanning and linear independence relating to something being a basis, like they both have to be true, and talking about that sort of whole Q greater than or equal to P thing. We talked about the number of vectors in a basis and how it makes sense. It's what we would intuitively think, like R3 has three dimensions. We talked about what a dimension is. We talked about defining the bases of the kernel image in two ways. One using the reducer echelon form, and one staying in the non-reducer echelon form, right? Both have their ups and downsides. One is more work for the image, one is more work for the kernel. And we talked about sort of generalizing those dimension theorems and stuff. We've got like the rank nullity theorem, the fundamental theorem of algebra, of linear algebra. We talked about the idea of collapsing and surviving dimensions. And then we moved into our last way of figuring out the bases in the image and kernel basis, which was the one where we look at sort of linear relations. And then finally, we talked about the fact that for something to be a basis, the vectors have to form an invertible matrix. So that is lesson 3.3. And next week, get excited because we have the very last lesson of 3.4, and then we're skipping very much ahead to lesson 6, because the way this textbook works is that after the first couple of chapters, you can kind of skip all around and it won't be too detrimental. And you can sort of pick what you want to focus on. So I hope you enjoyed this video, and thank you so much.